Picture this moment, if you will. Across the globe, people step outside for their morning routines and notice something impossible. There, blazing in the bright blue sky alongside our familiar sun, burns another star. Not the gentle twinkle of Venus, or the subtle glow of a distant planet, but a brilliant white point of light so intense it casts shadows on the ground below. Within hours, confusion spreads like wildfire across social media and news networks. Astronomers frantically check their instruments, while reporters speculate wildly about cosmic catastrophes. The internet explodes with theories ranging from alien invasions to the end of the world itself. Parents clutch their children closer as ancient fears of celestial omens resurface in the collective human consciousness. Some imagine waves of deadly radiation already washing over our planet, invisible and unstoppable. Others picture our atmosphere being stripped away like leaves in a cosmic hurricane. The new star seems to grow brighter by the hour, and with it, the terror that this celestial visitor heralds humanity's final chapter. Emergency services are overwhelmed with calls as people demand to know if they should flee, where they could possibly hide, whether there's any escape from whatever cosmic force has awakened in the heavens above. But here's what you need to understand. This dramatic scenario, this vision of worldwide panic and cosmic doom, represents exactly the kind of fear and misinformation that surrounds one of astronomy's most fascinating upcoming events. Because while a nearby star will indeed explode in our cosmic neighbourhood, the reality is far more wondrous and far less terrifying than our primitive instincts might suggest. Tonight, we're embarking on a journey to one of the most extraordinary objects in our night sky, a stellar giant that has captured human imagination for millennia and continues to perplex astronomers with its unpredictable behaviour. We're travelling to Betelgeuse, a red supergiant star that stands as one of nature's most magnificent time bombs, destined to end its life in one of the universe's most spectacular displays of cosmic violence. Before we dive deep into this stellar mystery, I'd love to know where you're watching from tonight, and whether you've ever spotted Betelgeuse glowing like a ruby ember in the constellation Orion. And if you find yourself drawn to these cosmic mysteries that challenge everything we think we know about our place in the universe, I'd be incredibly grateful if you gave this video a like and perhaps subscribe to join our community of stellar explorers. Get ready. The journey begins now. This is a story about a star that shouldn't exist according to everything we once believed about stellar evolution, yet blazes in our sky as a testament to the universe's capacity to surprise us. Betelgeuse represents something almost incomprehensible in its sheer scale and cosmic significance. When you look up at the constellation Orion on a clear winter evening, that distinctive reddish star marking the hunter's shoulder contains more mass than 15 of our suns combined. Yet it has somehow inflated to a size so enormous that if we could magically transport it to our solar system and place it where our sun currently resides, its outer atmosphere would engulf not just Mercury and Venus, but extend beyond Earth's orbit, past Mars, and stretch all the way out to Jupiter's path around what was once our sun. Think about that for a moment. This single star, visible to your naked eye from hundreds of light years away, could contain our entire inner solar system within its glowing envelope. The scale defies human comprehension, representing a ball of superheated plasma so vast that light itself takes over an hour to travel from one side to the other. Yet despite this tremendous size, Betelgeuse burns with a surface temperature cooler than our own sun, roughly 6,000 degrees Fahrenheit, compared to our sun's 10,000 degree surface, which explains its characteristic red glow that has mesmerized stargazers throughout human history. But Betelgeuse's story becomes even more extraordinary when we consider its age and evolutionary timeline. At approximately 10 million years old, this stellar giant is actually a cosmic infant compared to our nearly 5 billion-year-old sun. Yet while our Sun has billions of years of stable fusion ahead of it, Betelgeuse has already reached the final act of its stellar drama, having burned through its nuclear fuel at such a prodigious rate that it now faces imminent cosmic death. This apparent paradox reveals one of the fundamental principles governing stellar evolution throughout the universe. The most massive stars, those giants that capture our attention with their brilliant luminosity, are simultaneously the most short-lived. They burn bright and die young, consuming their nuclear fuel with such intensity that their lifespans are measured in millions rather than billions of years. Betelgeuse has already exhausted the hydrogen in its core and moved on to fusing increasingly heavier elements, each stage of fusion occurring more rapidly than the last as the star races toward its inevitable explosive finale. Recent astronomical discoveries have revolutionized our understanding of Betelgeuse's mysterious behavior and added fascinating complexity to its story. For years, astronomers noticed that this stellar giant exhibited puzzling variations in brightness, sometimes growing noticeably dimmer or brighter over periods of months or years. These fluctuations sparked intense speculation about whether they represented signs of an imminent stellar explosion, with some researchers suggesting that Betelgeuse might be approaching its final moments. The breakthrough came with the recent discovery that Betelgeuse isn't actually alone in its cosmic dance. Advanced observational techniques revealed the presence of a smaller companion star, a hot blue-white stellar body with roughly 1.5 times the mass of our Sun, orbiting Betelgeuse in a complex gravitational waltz that takes over 2,000 days to complete. This companion, invisible to casual observation due to its proximity to the brilliant red giant and its relatively faint luminosity compared to its massive partner, has been nicknamed Beetle Buddy by astronomers who spent years trying to confirm its existence. The discovery of this binary companion solved many of the mysteries surrounding Betelgeuse's erratic behavior. The periodic dimming that once seemed like harbingers of stellar doom now appears to result from dust clouds and gravitational interactions caused by the companion star's orbital dance around the red giant. As this smaller star follows its elongated orbit, it creates disturbances in Betelgeuse's outer atmosphere, triggering massive ejections of stellar material that temporarily obscure the giant star's brilliant surface from our earthbound perspective. This revelation fundamentally changed how astronomers interpret Betelgeuse's timeline for explosion. Rather than representing a star on the immediate verge of supernova, the brightness variations now appear to be part of a complex but stable system that could continue for potentially thousands of years before the final catastrophic collapse occurs. The companion star's presence also provides crucial insights into how massive stars evolve and die, offering a unique laboratory for studying binary stellar evolution in real time. The dramatic event known as the Great Dimming of Betelgeuse perfectly illustrates how this stellar system continues to surprise and educate astronomers. In late 2019, Betelgeuse suddenly became significantly fainter, losing nearly 2/3 of its normal brightness in what appeared to be an unprecedented stellar event. The dimming was so pronounced that even casual stargazers could notice the change with their naked eyes, leading to widespread speculation that the star might be preparing for its final explosive transformation. Space-based telescopes, including the Hubble Space Telescope, trained their sophisticated instruments on the dimming giant and revealed the true cause of this spectacular event. Rather than indicating imminent stellar collapse, the observations showed that Betelgeuse had literally blown its top, ejecting a massive cloud of stellar material from its surface in what astronomers termed a surface mass ejection. This explosion of stellar atmosphere created a vast dust cloud that temporarily blocked much of the star's light from reaching Earth, creating the illusion that the star itself was fading, when in reality it was simply hidden behind its own expelled material. The recovery of Betelgeuse's brightness over the following months confirmed that this was not a precursor to immediate explosion, but rather a demonstration of the violent atmospheric processes that characterize red supergiant stars in their final evolutionary phases. The event provided unprecedented insights into how massive stars shed material in their old age, offering a preview of the kinds of spectacular eruptions that might precede the eventual supernova explosion by decades or centuries. These observations revealed that Betelgeuse regularly undergoes cycles of expansion and contraction, pulsating like a cosmic heartbeat as it struggles to maintain equilibrium between the outward pressure of nuclear fusion and the inward pull of its own tremendous gravitational field. During these pulsations, the star's outer layers can expand to truly staggering proportions before contracting again, creating the brightness variations that have puzzled astronomers for generations. Understanding these pulsation cycles has become crucial for predicting when Betelgeuse might actually explode. Current estimates suggest that while the star will definitely undergo a supernova explosion at some point in its future, that moment could occur anywhere from tomorrow to 100,000 years from now. In cosmic terms, this represents the blink of an eye, but from a human perspective, it means that we might witness this spectacular event in our lifetimes, or it might remain a distant future occurrence for hundreds of generations to come. The challenge of measuring Betelgeuse's distance from Earth adds another layer of uncertainty to these predictions. Despite being one of our cosmic neighbours, determining the exact distance to this stellar giant has proven surprisingly difficult for astronomers. Different measurement techniques have produced results ranging from about 500 to over 800 light-years, with the current best estimate placing Betelgeuse at approximately 700 light-years from our solar system. This distance uncertainty matters enormously when calculating the potential effects of Betelgeuse's eventual explosion. A supernova at 500 light-years would have different implications for Earth than one at 800 light-years, affecting everything from the brightness of the explosion as seen from our planet to the amount of radiation and high-energy particles that might reach our atmosphere. The European Space Agency's Gaia mission, which has revolutionized our understanding of stellar distances throughout our galaxy, cannot provide measurements for Betelgeuse because the star is simply too bright for the spacecraft's sensitive instruments to observe directly. The physical processes occurring within Betelgeuse right now represent some of the most extreme physics in the known universe. Deep in the star's core, temperatures reach hundreds of millions of degrees, while pressures exceed anything achievable in terrestrial laboratories. Under these conditions, atomic nuclei that would normally repel each other with tremendous electromagnetic force are squeezed together with such violence that they overcome their natural repulsion and fuse together, releasing the enormous energies that power the star's luminosity. Betelgeuse has already progressed through the initial stages of this nuclear alchemy, having exhausted the hydrogen fuel that powers stars like our Sun for billions of years. The core now burns helium, fusing these lighter nuclei together to create carbon and oxygen in a process that releases less energy per reaction than hydrogen fusion. As the available helium fuel diminishes, the core will contract and heat up until it becomes hot enough to fuse carbon nuclei together, creating even heavier elements like neon and magnesium. This progression continues through successive stages of nuclear burning, with each phase occurring more rapidly than the last, as the star struggles to generate enough energy to support its enormous bulk against gravitational collapse. Silicon burning, the final stage of nuclear fusion that can provide energy to a massive star, produces iron nuclei in the core. But iron represents a nuclear dead end, the most stable element in the universe, which cannot be fused together to release additional energy. When Betelgeuse's core finally fills with iron, the stellar furnace that has burned for millions of years will suddenly shut down. Without the outward pressure of nuclear fusion to balance the inward pull of gravity, the core will begin to collapse in a process so rapid and violent that it defies human comprehension. In less than a second, A region the size of Earth will compress to a sphere only a few miles across, creating densities so extreme that atomic nuclei themselves are crushed together into an exotic form of matter found nowhere else in the universe. In the universe, the shockwave that emerges from this collapse carries with it energies that dwarf the combined power output of billions of suns, racing outward through Betelgeuse's layers at speeds of tens of thousands of kilometers per second. This expanding wall of superheated plasma encounters the star's outer envelope, the vast atmosphere that extends for hundreds of millions of kilometers into space, heating these outer layers to temperatures exceeding 100 billion degrees Fahrenheit. Under such extreme conditions, the normal rules of chemistry and physics break down completely. Atomic nuclei that have never before encountered each other in nature are suddenly forced together with such violence that they fuse into entirely new elements. The periodic table comes alive in Betelgeuse's death throes, as hydrogen and helium nuclei combine and recombine in countless permutations to create carbon, oxygen, silicon, sulfur, and dozens of other elements that cannot form under any other circumstances in the universe. But the nuclear alchemy doesn't stop there. The most exotic elements, those heavy atomic nuclei that require truly extraordinary conditions to form, emerge only in the final moments of the explosion. Gold, platinum, uranium, and other precious metals that we find on Earth today were forged in the hearts of ancient supernova, created when stellar shockwaves provided the incredible energies needed to build these complex atomic structures. The gold in your jewelry, the platinum in catalytic converters, even the uranium that powers nuclear reactors, all trace their origins to stellar explosions similar to the one that awaits Betelgeuse. This element forging process represents one of the most crucial roles that supernovae play in cosmic evolution. Before the first generation of massive stars lived and died, the universe contained only hydrogen and helium, the light elements created in the Big Bang itself. Every heavier element that makes planets possible, that enables the complex chemistry of life, had to be manufactured inside stellar cores and then dispersed through space by supernova explosions. The calcium in your bones was created in a dying star. The iron in your blood was forged in stellar cores that reached temperatures exceeding those found anywhere else in the universe. The oxygen you breathe with every inhalation represents the nuclear ash of ancient supernova, scattered through space billions of years ago, and eventually incorporated into the molecular clouds that gave birth to our solar system. We are, quite literally, made of star stuff, our very atoms carrying the memory of cosmic violence that occurred long before Earth existed. When Betelgeuse finally does explode, astronomers around the world will witness this element creation process in real time, observing through their telescopes as a single star briefly outshines an entire galaxy containing hundreds of billions of other suns. The explosion will be visible even during daylight hours, appearing as a brilliant white point of light, roughly half as bright as the full moon, concentrated into a stellar pinprick that will cast shadows at midnight and remain visible to the naked eye for months or even years. The first sign of this cosmic catastrophe won't arrive as visible light, however, but as an invisible flood of exotic particles called neutrinos. These ghostly messengers, so elusive that trillions pass through your body every second without any interaction whatsoever, will suddenly increase in intensity by factors of millions as Betelgeuse's core collapses. Massive underground detectors designed to catch these fleeting particles will register the neutrino burst hours or even days before the light of the explosion becomes visible, providing astronomers with an unprecedented early warning system for one of nature's most spectacular events. The neutrino detection represents far more than just an interesting scientific curiosity. These particles carry direct information about the physical processes occurring in Betelgeuse's core during the collapse, providing insights into physics under conditions so extreme that they cannot be replicated in any terrestrial laboratory. The temperature, density, and composition of the collapsing stellar core will be encoded in the energy spectrum and timing of the neutrino burst, offering scientists a unique window into the fundamental forces that govern matter under the most extreme conditions imaginable. Current neutrino detectors, massive underground installations filled with thousands of tons of ultra-pure water or other detection media, are already sensitive enough to register the flood of particles that will accompany Betelgeuse's explosion. When that moment arrives, these facilities will provide real-time monitoring of the core collapse process, allowing astronomers to track the formation of either a neutron star or black hole as it happens. The data gathered from this event will revolutionize our understanding of stellar death and provide crucial tests of theoretical models that have been developed over decades of research. The visual spectacle that follows the neutrino burst will transform the night sky in ways not seen for over 400 years. The last supernova visible to the naked eye occurred in 1604, when Johannes Kepler observed and documented what became known as Kepler's star. That explosion, located much farther from Earth than Betelgeuse, still shone brightly enough to be visible during daylight for several weeks and remained observable at night for over a year. Betelgeuse's proximity to Earth, combined with its massive size, suggests that its explosion will far exceed the brightness of Kepler's star. The supernova will likely reach a peak brightness comparable to Venus at its brightest, making it easily visible during daylight hours and casting distinct shadows at night. The concentrated nature of this light, focused into a single stellar point rather than spread across a disk like the Moon, will create an otherworldly appearance that will be impossible to ignore. The constellation Orion, one of the most recognizable star patterns in the night sky, will be permanently transformed by this event. For thousands of years, human cultures around the world have identified Betelgeuse as the distinctive reddish star marking Orion's shoulder, using it for navigation, timekeeping, and mythological storytelling. After the supernova fades, this familiar landmark will simply vanish, leaving future generations with a fundamentally different view of one of our most prominent constellations. But while the visual impact will be dramatic and the scientific value immeasurable, the question that concerns many people involves the potential effects on Earth itself. Popular culture and sensationalized media reports have often portrayed nearby supernova as existential threats to life on our planet, suggesting that the radiation and high-energy particles produced by these explosions could strip away our atmosphere, trigger mass extinctions, or otherwise devastate the biosphere. The reality, according to decades of careful scientific analysis, presents a far more reassuring picture. Betelgeuse's distance of approximately 700 light-years places it well outside the danger zone for any significant effects on Earth's environment or its inhabitants. Supernova only pose serious threats to planets within about 25 light-years of the explosion, a radius nearly 30 times smaller than our distance from Betelgeuse. The high-energy radiation produced by the supernova, while intense enough to be detected by sensitive instruments on Earth, will be far too diluted by the time it reaches our solar system to cause any meaningful damage to our atmosphere or biosphere. Gamma rays, X-rays, and other forms of electromagnetic radiation follow the inverse square law, meaning their intensity decreases with the square of the distance from their source. At Betelgeuse's distance, even the most energetic radiation will be reduced to levels comparable to natural background sources already present in space. The cosmic rays, high-energy particles, accelerated by the supernova shockwave, will indeed reach Earth's vicinity, but in quantities too small to overwhelm our planet's natural defenses. Earth's magnetic field and atmosphere already protect us from far more intense cosmic ray bombardment from other sources, including our own sun during solar flares. The additional cosmic rays from Betelgeuse will be measurable by scientific instruments, but will pose no threat to human health, technology, or the environment. Even the most exotic effects proposed by some researchers, such as temporary changes in atmospheric chemistry or subtle increases in cloud formation, would be too minor to affect weather patterns or climate on any meaningful scale. The robust nature of Earth's atmospheric and magnetic systems evolved over billions of years to handle far more severe cosmic bombardment, ensures that Betelgeuse's explosion will remain a spectacular astronomical event rather than a planetary catastrophe. This safety margin extends to our technological infrastructure as well. Satellites, power grids, and communication systems that might be vulnerable to intense electromagnetic pulses or radiation bursts will experience no significant effects from an explosion at Betelgeuse's distance. The most sensitive scientific instruments might detect subtle changes in background radiation levels, but these measurements will serve as valuable data points rather than indicators of impending technological failure. The timeline for Betelgeuse's explosion remains one of the most intriguing uncertainties in modern astronomy. While we know that the star has already entered the final phases of its evolution and will definitely explode as a supernova, predicting exactly when this event will occur challenges our current understanding of stellar physics. The processes governing the final stages of massive star evolution involve complex interactions between nuclear burning, gravitational collapse, rotation, magnetic fields, and mass loss that are difficult to model with precision. Current estimates place the explosion somewhere between tomorrow and 100,000 years in the future, a range that reflects both the inherent unpredictability of stellar evolution and the limitations of our observational capabilities. The recent discovery of Betelgeuse's binary companion has added new variables to these calculations, as the gravitational interactions between the two stars could either accelerate or delay the final collapse depending on their orbital dynamics and mass transfer rates. Some theoretical models suggest that the presence of a companion star might actually extend Betelgeuse's lifetime by providing additional fuel through mass transfer or by affecting the red giant's internal structure in ways that slow the progression toward core collapse. Other scenarios propose that tidal interactions could trigger instabilities that accelerate the star's death, potentially reducing the time until explosion by thousands of years. The observational evidence provides tantalizing clues, but no definitive answers. Betelgeuse's continued brightness variations, while now understood to result primarily from binary interactions rather than imminent collapse, still reflect genuine changes in the star's internal structure and energy production. Monitoring these fluctuations with increasingly sophisticated instruments offers our best hope for recognizing the subtle signs that might precede the final explosion by years or decades. Advanced computer simulations of massive star evolution, incorporating the latest understanding of nuclear physics, fluid dynamics, and stellar atmospheres, continue to refine our predictions about Betelgeuse's future. These models must account for the star's rotation, magnetic field strength, chemical composition, and the complex feedback mechanisms that govern energy transport from the core to the surface. Each refinement in these simulations brings us closer to understanding the precise conditions that will trigger the final collapse. The scientific community has developed comprehensive monitoring programs to track Betelgeuse's behavior across the electromagnetic spectrum. Ground-based telescopes continuously measure its brightness variations in visible light, while space-based observatories study its ultraviolet and X-ray emissions. Radio telescopes map the structure of the stellar atmosphere and detect molecular emissions from the star's outer layers. Infrared observations penetrate the dust clouds that sometimes obscure the star, revealing details about its surface temperature and mass loss rates. This multi-wavelength monitoring approach ensures that when Betelgeuse does begin its final collapse, astronomers worldwide will have as much advance warning as possible. The neutrino burst that precedes the visible explosion by hours or days will trigger automated alert systems that will immediately notify observatories around the globe, allowing them to train their instruments on the star before the light arrives. This coordination will enable unprecedented observations of a supernova from its very beginning, capturing details about the explosion mechanism that have never been observed before. The aftermath of Betelgeuse's explosion will provide scientists with a natural laboratory for studying some of the most extreme physics in the universe. The neutron star or black hole that forms from the collapsed core will represent matter compressed to densities exceeding that of atomic nuclei, creating conditions where the normal distinction between protons and neutrons breaks down completely. Studying these exotic objects tests our understanding of fundamental physics under conditions that can never be replicated on Earth. The expanding supernova remnant, the glowing shell of ejected stellar material racing outward at thousands of kilometers per second, will continue to evolve and provide scientific insights for centuries after the initial explosion. As this material collides with the interstellar medium, it will create shockwaves that accelerate particles to tremendous energies, contributing to the cosmic ray background that permeates our galaxy. The chemical elements forged in Betelgeuse's final moments will gradually mix with the surrounding gas clouds, enriching them with heavy elements that will eventually be incorporated into future generations of stars and planets. The expanding shockwave from Betelgeuse's explosion will serve as a cosmic laboratory for understanding how heavy elements disperse throughout the galaxy. As this wall of superheated plasma encounters the thin gas that fills interstellar space, it will compress and heat this material to millions of degrees, creating conditions similar to those found in the most powerful particle accelerators on Earth. The collision will generate intense magnetic fields that accelerate charged particles to near light speed, contributing to the galactic cosmic ray background that has influenced planetary evolution throughout the Milky Way's history. These cosmic rays, high-energy protons, and heavier atomic nuclei moving at substantial fractions of light speed play crucial roles in galactic chemistry and stellar formation. They trigger nuclear reactions in interstellar gas clouds, creating rare isotopes that serve as tracers for astronomical processes. They influence the formation of new stars by affecting the ionization balance in molecular clouds, determining how efficiently gravity can overcome thermal pressure to trigger collapse. The cosmic rays produced by Betelgeuse's explosion will continue circulating through our galaxy for millions of years, carrying the star's nuclear products to distant regions where they might eventually seed the formation of new planetary systems. The neutron star that will likely form from Betelgeuse's collapsed core represents one of the most extreme objects in the known universe. In a sphere barely 20 kilometers across, the mass of 1.5 suns will be compressed to densities exceeding that of atomic nuclei themselves. Under these conditions, the normal structure of matter breaks down completely. Protons and electrons are crushed together to form neutrons, while the neutrons themselves are packed so tightly that they touch, creating a giant atomic nucleus the size of a mountain. The magnetic field generated by this spinning neutron star will exceed Earth's magnetic field by factors of trillions, strong enough to distort the very atoms in its vicinity. As the neutron star rotates, potentially hundreds of times per second, it will sweep beams of electromagnetic radiation across space like a cosmic lighthouse. If Earth happens to lie in the path of these beams, radio telescopes will detect regular pulses with timing precision that rivals the most accurate atomic clocks ever built. These pulsar signals provide astronomers with unprecedented tools for studying fundamental physics. The extreme gravitational fields near neutron stars bend space and time in ways predicted by Einstein's general relativity, allowing scientists to test these theories under conditions impossible to replicate in terrestrial laboratories. The neutron star's rotation gradually slows over time as it loses energy through electromagnetic radiation, and precise measurements of this spin-down reveal details about the star's internal structure and the exotic forms of matter that exist at nuclear densities. Some theoretical models suggest that neutron star cores might contain even stranger forms of matter, including quark matter, where the normal boundaries between protons and neutrons dissolve entirely, or exotic particles that exist nowhere else in the universe. The neutron star formed from Betelgeuse's collapse will provide a natural laboratory for investigating these possibilities, potentially revealing new physics that could revolutionize our understanding of the fundamental forces governing matter and energy. The visual transformation of Betelgeuse from red supergiant to brilliant supernova will unfold over a timescale that allows detailed astronomical observation of every phase. Unlike more distant stellar explosions that appear as brief flashes of light, Betelgeuse's proximity ensures that its supernova will remain visible to the naked eye for months, possibly years, providing an extended opportunity for scientific study. During the first few weeks after the explosion becomes visible, the supernova's brightness will continue increasing as the shockwave propagates through the star's extended atmosphere. Spectroscopic observations during this phase will reveal the chemical composition of Betelgeuse's outer layers, providing direct measurements of the elements synthesized during the star's lifetime. These observations will test theoretical models of stellar nucleosynthesis and reveal how massive stars distribute different elements throughout their atmospheric layers. As the supernova reaches peak brightness, roughly 2 weeks after the initial explosion, it will shine with the combined luminosity of hundreds of millions of suns. The concentrated nature of this light, focused into a single stellar point, rather than distributed across a disk like the Moon, will create an otherworldly appearance unlike anything seen in recorded human history. The supernova will cast distinct shadows at night and remain easily visible during daylight hours, fundamentally altering the appearance of the night sky for observers across Earth. The decline phase of the supernova, extending over months and years, will be powered by the radioactive decay of unstable isotopes created during the explosion. Nickel-56, produced in the final moments of nuclear burning, will decay to cobalt-56, and then to stable iron-56, releasing gamma rays and positrons that heat the expanding debris and maintain its luminosity. Astronomical observations of this decline will provide direct measurements of the quantities of radioactive elements produced, testing our understanding of explosive nucleosynthesis. Advanced space-based telescopes will capture images showing the expansion of the supernova debris in real time, revealing the three-dimensional structure of the explosion and the interactions between the shockwave and any circumstellar material ejected by Betelgeuse during its red supergiant phase. These observations will help astronomers understand how massive stars lose mass in their final evolutionary stages and how this mass loss affects the supernova explosion mechanism. The supernova remnant that emerges from this explosion will continue evolving for thousands of years, gradually transitioning from a hot, expanding bubble of stellar debris to a mature nebula enriched with heavy elements. Ground-based and space-based observatories will monitor this evolution, watching as the shockwave sweeps up interstellar material and creates the complex filamentary structures characteristic of old supernova remnants. The Crab Nebula, the remnant of a supernova observed by Chinese astronomers in 1054, provides a preview of what Betelgeuse's explosion site might look like a millennium from now. This beautiful, expanding cloud of glowing gas spans several light years and continues growing at speeds of over 1,000 kilometers per second. At its center, a rapidly spinning neutron star powers the nebula's emission through magnetic field interactions that accelerate particles to tremendous energies. The elements forged in Betelgeuse's explosion will eventually mix with the surrounding interstellar medium, enriching it with carbon, oxygen, silicon, sulfur, iron, and dozens of other elements essential for planet formation and the chemistry of life. These materials will be incorporated into future generations of stars and planetary systems, potentially enabling the formation of rocky worlds with the chemical diversity necessary to support complex biological processes. Current models of galactic chemical evolution suggest that supernovae from massive stars like Betelgeuse are the primary source of many elements heavier than helium. Without these stellar explosions, the universe would remain composed almost entirely of hydrogen and helium, with no mechanism for creating the carbon in organic molecules, the oxygen in water, or the silicon in rocky planets. Every supernova represents a crucial step in the cosmic recycling program that has gradually enriched our galaxy with the materials needed for complexity and life. The scientific impact of observing Betelgeuse's supernova will extend far beyond stellar astronomy into multiple areas of physics and cosmology. The explosion will provide the first opportunity to study a core collapse supernova with modern instrumentation from beginning to end, potentially resolving long-standing questions about the explosion mechanism and the conditions required for successful shockwave propagation. Theoretical models of core collapse supernovae still struggle to explain how the initial shockwave, formed when the stellar core rebounds from collapse, manages to propagate through the star's outer layers without stalling. Computer simulations suggest that neutrino heating, magnetic fields, or rotation might be necessary to revive the stalled shock, but direct observational evidence has been lacking. Betelgeuse's explosion will provide crucial data to test these theoretical models and determine which physical processes actually drive successful supernova explosions. The neutrino observations will be particularly valuable for understanding the core collapse process itself. Current neutrino detectors are sensitive enough to measure not just the total energy released in neutrinos, but also the time evolution and energy spectrum of the neutrino burst. These measurements will reveal details about the formation of the neutron star, including its initial temperature, composition, and rotation rate. Underground neutrino observatories around the world have established automated alert systems that will immediately notify the global astronomical community when the neutrino burst is detected. This early warning system will ensure that telescopes worldwide can be pointed at Betelgeuse before the optical explosion becomes visible, capturing the very first moments of the shockwave breakout from the stellar surface. The gravitational wave detectors that have revolutionized astronomy in recent years might also detect signals from Betelgeuse's core collapse. While spherically symmetric collapse would produce no gravitational waves, any asymmetries in the collapsing core or the formation of the neutron star could generate detectable ripples in spacetime. These observations would provide an entirely independent probe of the explosion mechanism and the extreme physics operating during core collapse. The multi-messenger astronomy approach, combining neutrino detections, gravitational wave observations, electromagnetic radiation across all wavelengths and cosmic ray measurements, will provide an unprecedented comprehensive view of a stellar explosion. This coordinated observational campaign will generate data that astronomers will be analysing for decades, potentially revealing new physics and advancing our understanding of stellar evolution, nuclear processes, and fundamental forces. The cultural and historical significance of witnessing Betelgeuse's explosion cannot be understated. This event will represent the first nearby supernova visible to the naked eye in over 4 centuries, making it a once-in-multiple-lifetimes astronomical spectacle. Unlike the supernovae observed by historical astronomers who lacked modern theoretical frameworks to understand what they were seeing, contemporary observers will witness this event with full knowledge of the physical processes involved. The explosion will provide a direct visceral connection to the cosmic processes that created the elements in our bodies and enabled the existence of rocky planets throughout the universe. Every person who looks up at the supernova will be seeing the very mechanism that forged the calcium in their bones, the iron in their blood, and the oxygen they breathe. This tangible link between stellar death and terrestrial life will offer profound perspectives on humanity's cosmic connections. Educational institutions worldwide will undoubtedly incorporate Betelgeuse's supernova into their curricula, using this real-time demonstration of stellar evolution to teach students about nuclear physics, stellar astronomy, and the cosmic origins of the chemical elements. The event will likely inspire a new generation of scientists and engineers, much as the Apollo moon landings motivated careers in aerospace and space exploration. The supernova will also serve as a natural experiment in science communication and public understanding of astronomy. Unlike many astronomical discoveries that require sophisticated instruments to detect and complex theories to interpret, Betelgeuse's explosion will be immediately apparent to anyone who looks up at the night sky. This accessibility will provide astronomers with an unprecedented opportunity to engage the public in real science, demonstrating how astronomical observations lead to deeper understanding of cosmic processes. The global nature of the observation will emphasize the universal human experience of wonder at cosmic phenomena. People across every continent, culture, and background will share the same spectacular view, potentially fostering greater appreciation for our common heritage as citizens of a universe filled with magnificent and ongoing creative processes. The supernova will serve as a reminder that Earth exists within a vast cosmic ecosystem where stellar birth, death, and rebirth drive the chemical evolution that makes life possible. Amateur astronomers will play important roles in monitoring Betelgeuse's explosion and its aftermath. The brightness and duration of the supernova will make it accessible to modest telescopes and even careful naked-eye observations, allowing citizen scientists to contribute meaningful data to professional research efforts. Variable star observation networks already exist to monitor stellar brightness changes, and these groups will provide valuable long-term monitoring of the supernova's decline phase. Photography enthusiasts will capture images that document this historic event for future generations, creating a visual record of the supernova's appearance from locations around the world. These images will serve not just as beautiful art, but as scientific data showing how atmospheric conditions, light pollution, and observing techniques affect the visibility of astronomical objects. The economic impact of Betelgeuse's supernova will likely extend beyond the scientific community into tourism, education, and technology sectors. Dark sky locations that offer optimal viewing conditions may experience increased visitor traffic as people travel to witness this cosmic spectacle under the best possible conditions. Planetariums and science museums will develop special programs and exhibits to help visitors understand and appreciate the significance of what they're observing. Technology companies might develop new applications and devices to help people locate and observe the supernova, potentially spurring innovations in consumer astronomy equipment. The event could catalyze increased funding for astronomical research and space-based observatories as public interest in astronomy reaches levels not seen since the early days of space exploration. The long-term legacy of Betelgeuse's supernova will depend partly on how effectively the scientific community communicates the significance of this event to the general public. Unlike many astronomical discoveries that remain confined to specialized journals and conferences, this supernova will demand public attention and provide a unique opportunity to share the wonder and importance of scientific discovery with a global audience. The timing of when Betelgeuse actually explodes will determine which generation of humans witnesses this spectacular event. Current astronomical observations suggest the explosion could occur at any time within the next several thousand years, but the inherent unpredictability of stellar evolution makes precise timing impossible. The star's recent behavioral changes, while now understood to result from binary interactions rather than an imminent collapse, continue to provide valuable data about the final stages of massive star evolution. Regardless of exactly when it occurs, Betelgeuse's supernova will represent a culminating moment in humanity's long relationship with this remarkable star. For thousands of years, human cultures have incorporated Betelgeuse into their mythologies, navigation systems, and calendar keeping. The star has served as a seasonal marker, a navigational reference, and a source of wonder for countless generations of observers who had no understanding of its true nature as a dying stellar giant. The explosion will mark the end of this ancient relationship, while simultaneously beginning a new chapter in our cosmic story. Future generations will inherit a fundamentally different night sky, one where Orion's familiar outline has been permanently altered by the disappearance of its distinctive reddish shoulder star. But they will also inherit the scientific knowledge gained from observing this cosmic transformation, along with the deeper understanding of stellar evolution and galactic chemical enrichment that this event will provide. The neutron star, or black hole, that remains after Betelgeuse's explosion will continue influencing its cosmic neighborhood for millions of years to come. If it forms a pulsar, its rotating beams of electromagnetic radiation will sweep across space with clockwork precision, potentially serving as cosmic lighthouses for future interstellar navigation. The supernova remnant will continue expanding and evolving, creating a lasting monument to this stellar giant's dramatic final act. Scientific observations of Betelgeuse and similar red supergiant stars will continue advancing our understanding of stellar evolution and the processes that determine which massive stars explode as supernovae. Each new measurement of the star's properties, each refinement in theoretical models, and each improvement in observational techniques brings astronomers closer to predicting the exact timing and characteristics of future supernova explosions. The knowledge gained from studying Betelgeuse will inform our understanding of stellar explosions throughout the universe, helping astronomers interpret observations of distant supernova in other galaxies and refine models of cosmic chemical evolution. This research has practical applications for understanding the formation of planetary systems, the distribution of heavy elements throughout the cosmos, and the conditions necessary for the emergence of life on other worlds. As we continue monitoring Betelgeuse's behavior and preparing for its eventual explosion, we participate in one of astronomy's most exciting ongoing investigations. This red supergiant star represents a natural laboratory for studying extreme physics under conditions that cannot be replicated anywhere else, offering insights into fundamental processes that shape the evolution of galaxies and the chemical composition of the universe itself. The story of Betelgeuse reminds us that we live in a dynamic, evolving cosmos where even the most stable appearing objects undergo dramatic transformations over cosmic timescales. Stars are born, live, and die according to physical laws that operate with remarkable consistency throughout the observable universe, yet each stellar explosion is unique in its details and consequences. Betelgeuse's supernova will add another chapter to this ongoing story of cosmic evolution, providing new insights into how the universe continuously recreates itself through cycles of stellar death and renewal. The expanding debris field from Betelgeuse's explosion will serve as a cosmic particle accelerator, creating conditions that dwarf the capabilities of any human-built machine. As the shockwave races outward, at velocities approaching 30,000 kilometers per second, it will encounter the thin wisps of gas and dust that Betelgeuse has been shedding for millennia during its red supergiant phase. This collision between the high-speed ejector and the circumstellar material will generate temperatures exceeding 10 million degrees and magnetic fields thousands of times stronger than anything found in our solar system. Within this extreme environment, atomic nuclei will be accelerated to energies that approach significant fractions of light speed, creating cosmic rays that will propagate throughout our galactic neighborhood for millions of years. These high-energy particles represent more than just exotic physics phenomena. They carry the chemical fingerprints of Betelgeuse's nuclear furnace, spreading the elements forged in the star's final moments across vast distances and seeding the raw materials for future planetary systems. The shockwave's interaction with Betelgeuse's surrounding environment will also reveal the hidden history of the star's mass loss over the past several 100,000 years. Astronomers expect to observe complex shell structures and asymmetric features in the expanding debris, created as the explosion encounters density variations in the circumstellar medium. These observations will provide unprecedented insights into how massive stars shed material in their final evolutionary phases and how this mass loss affects the ultimate supernova explosion. Advanced computer models predict that the shockwave will continue accelerating material for decades after the initial explosion, creating a multi-temperature plasma environment where different regions emit radiation across the entire electromagnetic spectrum. Radio telescopes will detect synchrotron emission from relativistic electrons spiraling in the shock's magnetic field. X-ray observatories will map the hot plasma created by the collision between ejecta and circumstellar material. Optical telescopes will capture the visible light produced as the shockwave ionizes hydrogen and heavier elements in the surrounding medium. These multi-wavelength observations will allow astronomers to construct detailed three-dimensional maps of the explosion and its aftermath, revealing how energy and momentum transfer from the collapsed core to the star's outer layers. Current theoretical models struggle to explain exactly how the initial shockwave, formed during core collapse, manages to propagate successfully through the star's extended envelope without stalling. Betelgeuse's explosion will provide crucial observational data to test these models and determine which physical mechanisms enable successful shockwave breakout. The neutrino signal from Betelgeuse's core collapse will arrive at Earth carrying information about physical processes occurring under conditions so extreme that they cannot be studied in any terrestrial laboratory. When the stellar core reaches nuclear density and rebounds from collapse, it will release more energy in neutrinos during 10 seconds than our Sun produces in electromagnetic radiation over its entire 10 billion year lifetime. This neutrino burst will provide direct observations of matter transitioning from normal atomic structure to the exotic states found inside neutron stars. Underground neutrino detectors distributed around the globe will measure not just the total energy of this burst, but also its detailed time structure and energy spectrum. These measurements will reveal the core's temperature evolution during collapse, the efficiency of neutron formation, and potentially the initial properties of the newly formed neutron star. If the core collapse produces a black hole instead of a neutron star, the neutrino signal will exhibit different characteristics that could provide our first direct observations of black hole formation in real time. The sensitivity of current neutrino detection facilities represents a remarkable achievement in experimental physics. These underground installations, shielded from cosmic radiation by thousands of meters of rock, can detect individual neutrino interactions in volumes containing tens of thousands of tons of ultra-pure water or liquid scintillator. When Betelgeuse's neutrino burst arrives, these detectors will register millions of interactions within the span of seconds, creating a detailed record of the core collapse process with temporal resolution measured in milliseconds. The gravitational wave observatories that have revolutionized astronomy over the past decade may also detect signals from Betelgeuse's explosion. While perfectly spherical core collapse would produce no gravitational waves, realistic models predict that various asymmetries could generate detectable spacetime ripples. Convective instabilities in the collapsing core, rotation effects, or the formation and subsequent evolution of the neutron star could all contribute to gravitational wave emission. These potential gravitational wave signals would provide an entirely independent probe of the explosion mechanism, revealing details about the core collapse process that cannot be observed through electromagnetic radiation or neutrinos. The combination of gravitational waves, neutrinos, and electromagnetic observations represents the multi-messenger astronomy approach that has already provided revolutionary insights into neutron star mergers and other extreme cosmic events. The electromagnetic fireworks that follow core collapse will unfold over timescales ranging from seconds to centuries, each phase revealing different aspects of the explosion physics. The initial shockwave breakout, when the rebounding core's energy finally reaches the stellar surface, will produce a brief but intense flash of X-ray and gamma-ray radiation. This breakout signal, lasting only minutes, will provide direct measurements of the shockwave's energy and the density structure of Betelgeuse's outer atmosphere. Following shock breakout, the supernova will enter its plateau phase, during which the expanding debris will remain hot and luminous for several months. This sustained brightness results from the shockwave's continued interaction with Betelgeuse's extended hydrogen envelope, which contains enough material to power the supernova's luminosity long after the initial explosion energy has been deposited. Spectroscopic observations during this phase will map the distribution of different elements throughout the stellar envelope, testing theoretical predictions about how massive stars stratify their composition during evolution. The transition from plateau to decline phase marks another crucial period for understanding supernova physics. As the hydrogen envelope becomes optically thin and ceases to trap the explosion's energy, the supernova's light curve will be powered primarily by radioactive decay of unstable isotopes created during the explosion. The most important of these is nickel-56, which decays through cobalt-56 to stable iron-56 with a half-life that closely matches the observed decline rates of many supernovae. Detailed observations of this radioactive decay phase will provide direct measurements of the quantities of different isotopes produced during explosive nucleosynthesis. These measurements will test theoretical models of how shockwaves trigger nuclear reactions in stellar material and determine the efficiency with which supernovae create elements heavier than iron. The data will also constrain models of the explosion mechanism by revealing how thoroughly the shockwave mixed different layers of the stellar interior. Advanced space-based telescopes will capture images showing the physical expansion of the supernova debris, potentially resolving structural details as small as individual clumps and filaments within the ejector. These observations will reveal the three-dimensional geometry of the explosion and test whether the shockwave propagated symmetrically or developed significant asymmetries due to rotation, magnetic fields, or pre-existing density variations in the stellar envelope. The Hubble Space Telescope has already demonstrated the capability to resolve expanding supernova remnants in nearby galaxies, revealing complex filamentary structures and shock-heated regions within the debris. For a supernova at Betelgeuse's distance, next-generation space telescopes will provide even more detailed imaging, potentially tracking the expansion of individual features within the ejector over periods of years or decades. These high-resolution observations will also search for evidence of the compact object left behind by core collapse. If Betelgeuse's core forms a neutron star, it may be detectable as a pulsar, emitting regular pulses of electromagnetic radiation as it spins. The timing and characteristics of these pulses would provide direct measurements of the neutron star's rotation rate, magnetic field strength, and potentially its internal structure. If the core collapse produces a black hole instead of a neutron star, the observational signatures would be quite different. Black holes do not emit regular pulses like pulsars, but they can be detected through their gravitational effects on surrounding material or through X-ray emission from any matter that falls into their vicinity. The formation of a black hole from Betelgeuse's core would represent one of the most massive stellar mass black holes ever observed, providing crucial data for understanding the relationship between stellar mass and the nature of core collapse outcomes. The chemical inventory dispersed by Betelgeuse's explosion will enrich the surrounding interstellar medium with elements that are essential for planet formation and potentially for life itself. Spectroscopic analysis of the expanding debris will reveal the quantities of carbon, oxygen, neon, magnesium, silicon, sulfur, calcium, and iron produced during the star's lifetime and during the final explosive moments. These measurements will provide direct tests of stellar nucleosynthesis theory and constrain models of how different stellar masses contribute to galactic chemical evolution. The explosion will also produce significant quantities of radioactive isotopes that decay over timescales ranging from days to millions of years. Some of these, like aluminum-26 and iron-60, have been detected in meteorites and deep-sea sediments on Earth, providing evidence of past supernova explosions in our galactic neighborhood. Betelgeuse's explosion will add to this radioactive inventory, creating isotopic signatures that may be detectable in future solar system materials. The mixing and distribution of these elements throughout the surrounding region will be influenced by the complex fluid dynamics of the expanding supernova remnant. Rayleigh-Taylor instabilities at the interface between different density regions will create finger-like projections that enhance the mixing of materials from different parts of the original star. These mixing processes determine how efficiently supernova explosions distribute their chemical products, and how quickly these materials become available for incorporation into new stellar and planetary systems. The long-term evolution of Betelgeuse's supernova remnant will create a lasting monument to this stellar giant's explosive death. Over thousands of years, the expanding shockwave will sweep up increasing amounts of interstellar material, eventually accumulating several solar masses of gas and dust from the surrounding medium. This accumulated material will be heated, compressed, and accelerated by the ongoing expansion, creating the complex shell structures characteristic of mature supernova remnants. The Crab Nebula provides an excellent preview of what Betelgeuse's explosion site might look like a millennium from now. This remarkable object, the remnant of a supernova observed by Chinese astronomers in 1054, continues expanding at over 1,000 kilometers per second while being powered by a rapidly spinning neutron star at its center. The neutron star's strong magnetic field and rapid rotation create a pulsar wind that inflates the surrounding nebula and powers its emission across the electromagnetic spectrum. Detailed studies of the Crab Nebula have revealed intricate filamentary structures created by the interaction between the pulsar wind and the expanding supernova debris. These observations suggest that Betelgeuse's remnant will similarly develop complex internal structures as the central compact object interacts with the surrounding material. The specific characteristics will depend on whether the core collapse produces a neutron star or black hole, and on the properties of the surrounding interstellar medium. The supernova remnant will continue influencing its cosmic environment for hundreds of thousands of years, serving as a source of cosmic rays, a driver of interstellar turbulence, and a contributor to the heating and ionization of the surrounding gas. These effects help regulate star formation in the galaxy by affecting the thermal and chemical properties of molecular clouds when new stars are born. The energy input from supernova explosions is crucial for maintaining the observed structure and dynamics of the interstellar medium. Educational institutions worldwide will undoubtedly develop comprehensive programs to help students understand and appreciate Betelgeuse's explosion when it occurs. This event will provide an unparalleled opportunity to demonstrate the connections between stellar evolution, nuclear physics, and cosmic chemical evolution using real-time observations rather than theoretical models or computer simulations. Students will witness the actual processes that created the elements in their bodies and enabled the formation of rocky planets throughout the universe. The supernova will also serve as a natural laboratory for testing and refining theoretical models of stellar evolution and explosion physics. Current models must make numerous assumptions about poorly understood processes like convection, rotation, magnetic fields, and mass loss rates. Detailed observations of Betelgeuse's explosion will provide crucial data to validate or revise these theoretical frameworks, potentially leading to improved predictions for other massive stars approaching the ends of their lives. The global coordination required for comprehensive supernova observations will demonstrate the international nature of modern astronomical research. Observatories on every continent will contribute data across the electromagnetic spectrum, while underground neutrino detectors and gravitational wave observatories provide complementary information about the explosion mechanism. This collaborative effort will generate datasets that astronomers will analyze for decades to come. The technological capabilities available for studying Betelgeuse's supernova far exceed those that existed during the last nearby stellar explosion over 4 centuries ago. Modern CCD cameras, spectrographs, and space-based telescopes can detect and analyze radiation across wavelengths from radio waves to gamma rays with sensitivities and spectral resolution that would have seemed impossible to earlier generations of astronomers. These advanced instruments will capture details about the explosion that could never have been observed using historical techniques. Machine learning and artificial intelligence tools are already being developed to help astronomers analyze the enormous datasets that will be generated by supernova observations. These computational approaches can identify subtle patterns and correlations in multi-wavelength data that might escape human analysis, potentially revealing new insights about explosion physics and stellar evolution. The combination of unprecedented observational capabilities and advanced analysis techniques ensures that Betelgeuse's supernova will advance our understanding of stellar death in ways that previous generations of astronomers could never have anticipated. The cultural impact of witnessing a nearby supernova will extend far beyond the scientific community. This spectacular astronomical event will provide a shared global experience that transcends national, cultural, and linguistic boundaries. People worldwide will look up at the same brilliant point of light and contemplate the cosmic processes that created the elements essential for life. This common experience may foster greater appreciation for our shared heritage as products of stellar evolution and our common dependence on the cosmic processes that continue shaping the universe around us. The supernova will also challenge common misconceptions about astronomical timescales and the dynamic nature of the cosmos. Many people think of stars as eternal, unchanging fixtures in the night sky, unaware that even the most massive stars have finite lifetimes measured in millions, rather than billions of years. Betelgeuse's dramatic transformation will demonstrate that the universe remains active and evolving, with ongoing processes that dwarf human timescales, yet operate according to physical laws that human intelligence can understand and predict. Photography enthusiasts and amateur astronomers will play important roles in documenting this historic event for future generations. The brightness and extended duration of the supernova will make it accessible to modest equipment, allowing citizen scientists to contribute meaningful observations to professional research efforts. These contributions will provide valuable data about the supernova's behavior while engaging the public in authentic scientific investigation. The economic implications of Betelgeuse's supernova will likely extend into multiple sectors beyond astronomy. Tourism to dark sky locations may increase as people seek optimal viewing conditions for this once-in-multiple-lifetimes event. Educational institutions may experience increased enrollment in astronomy and physics programs as the supernova inspires new interest in scientific careers. Technology companies may develop new applications and equipment to help people observe and understand the astronomical spectacle. The timing uncertainty surrounding Betelgeuse's explosion means that any generation could be the one to witness this remarkable event, Current observations cannot predict whether the supernova will occur next year or several thousand years from now. This uncertainty adds an element of anticipation to astronomical observations of Betelgeuse, as each brightness fluctuation or spectroscopic change could potentially signal the beginning of the final collapse sequence. Regardless of exactly when it occurs, Betelgeuse's supernova will represent a culminating moment in humanity's evolving relationship with this stellar giant. For millennia, human cultures have incorporated this distinctive red star into their mythologies, navigation systems, and seasonal calendars. The explosion will mark the end of this ancient familiarity, while simultaneously providing unprecedented insights into the physical processes that govern stellar evolution throughout the universe. The neutron star, or black hole, that remains after the explosion will continue influencing its cosmic environment for millions of years to come. These compact objects represent the ultimate expression of gravitational collapse, creating conditions where matter exists in states so extreme that they test the fundamental limits of our understanding of physics. Studying these remnants provides unique opportunities to investigate the behavior of matter and energy under conditions that can never be replicated in terrestrial laboratories. Future space missions may eventually visit the Betelgeuse supernova remnant directly, using advanced propulsion technologies to study the explosion site and its compact central object up close. Such missions would provide unprecedented detail about the explosion's three-dimensional structure and the properties of the neutron star or black hole formed during core collapse. These observations could revolutionize our understanding of stellar death and the exotic physics operating in the most extreme gravitational environments in the universe. The knowledge gained from studying Betelgeuse will inform our interpretation of stellar explosions observed throughout the cosmos. Supernovae in distant galaxies appear as brief flashes of light that provide limited information about the explosion mechanism and stellar properties. The detailed observations possible for a nearby explosion like Betelgeuse will provide crucial calibration data for understanding these more distant events and their roles in cosmic evolution. As we continue monitoring Betelgeuse and preparing for its eventual explosion, we participate in one of astronomy's most exciting ongoing investigations. This red supergiant star represents a natural laboratory for studying extreme stellar physics under conditions that reveal fundamental truths about how massive stars live, die, and enrich the cosmos with heavy elements. The explosion, whenever it occurs, will provide answers to questions that have puzzled astronomers for generations, while undoubtedly raising new mysteries that will drive future research. The story of Betelgeuse reminds us that we inhabit a universe where even the most apparently stable objects undergo dramatic transformations over cosmic time. Stars are born from collapsing gas clouds, live their lives according to the laws of nuclear physics, and die in spectacular explosions that seed space with the materials necessary for planets and life. These cycles of stellar birth, evolution, and death have been operating for billions of years, gradually increasing the chemical complexity of the universe and creating the conditions that made our existence possible. Betelgeuse's eventual supernova will add another chapter to this ongoing story of cosmic evolution, demonstrating once again that we live in a dynamic universe where creative and destructive processes operate on scales that challenge human imagination. The explosion will serve as a reminder that Earth and its inhabitants exist within a vast cosmic ecosystem where stellar death enables new forms of complexity and beauty to emerge over timescales that span the history of the universe itself. The truth about what we would actually experience extends far beyond the simple spectacle of a new bright star appearing in our daytime sky. When Betelgeuse finally reaches the end of its stellar journey and undergoes core collapse, Earth will witness an astronomical event that unfolds across multiple phases, each offering unique scientific opportunities and visual experiences that will captivate observers for months or potentially years. The initial detection will come not through human eyes or conventional telescopes, but through sensitive, underground facilities designed to catch the most elusive particles in the universe. Neutrino observatories, buried beneath mountains and ocean floors around the globe, will suddenly register an unprecedented flood of these ghostly messengers, billions upon billions of them streaming through Earth every second as Betelgeuse's core compresses from the size of our planet to a sphere barely 20 kilometers across in less than a second. These neutrinos carry the first news of the stellar catastrophe, racing ahead of the light by hours or even days, because they can escape directly from the collapsing core while photons must fight their way through the star's dense outer layers. The neutrino burst represents more than just an early warning system for astronomers. It provides a direct window into the most extreme physics imaginable, where matter reaches densities exceeding atomic nuclei and temperatures soar beyond 100 billion degrees. Underground detectors containing tens of thousands of tons of ultra-pure water will capture millions of these neutrino interactions within seconds, creating detailed records of the core collapse process with temporal precision measured in milliseconds. Scientists will analyze the energy spectrum and timing of this burst to determine whether Betelgeuse's core forms a neutron star or collapses completely into a black hole, providing crucial tests of theories about stellar death that have been developed over decades of research. When the light finally breaks free from Betelgeuse's surface and begins its journey across the 700 light-years to Earth, it will announce itself with a sudden brightening that transforms the familiar red giant into something entirely unprecedented in modern human experience. The initial shock breakout, lasting only hours, will flood space with X-rays and gamma radiation as the rebounding core's energy finally reaches the stellar surface, after fighting through hundreds of millions of kilometers of dense stellar material. Ground-based and space-based observatories will detect this initial flash across multiple wavelengths simultaneously, providing real-time measurements of the shockwave's energy and the structure of Betelgeuse's outer atmosphere. The X-ray emissions will reveal temperatures exceeding millions of degrees as the shockwave ionizes and heats the stellar material, while radio telescopes detect the characteristic signatures of electrons accelerated to tremendous speeds by the explosion's magnetic fields. Following this initial burst, Betelgeuse will enter what astronomers call the plateau phase, a period of sustained maximum brightness that could last several weeks as the shockwave continues propagating through the star's extended hydrogen envelope. During this spectacular interval, the supernova will shine with roughly half the brightness of the full moon, concentrated into a single, brilliant point that casts distinct shadows at midnight and remains easily visible throughout the day. The visual impact during this plateau phase will be unlike anything experienced in recorded human history. Ancient Chinese astronomers described similar brightness levels for the supernova that created the Crab Nebula, noting that the stellar explosion remained visible during daylight for nearly a month and continued glowing in the night sky for almost 2 years. Betelgeuse's proximity and massive size suggest its explosion will equal or exceed these historical accounts, creating a celestial beacon that fundamentally alters the appearance of the night sky. Spectroscopic observations during the plateau phase will reveal the chemical composition of Betelgeuse's outer layers with unprecedented detail, mapping the distribution of hydrogen, helium, carbon, oxygen, and heavier elements throughout the stellar envelope. These measurements will test theoretical models of how massive stars stratify their composition during evolution and provide direct evidence of the nuclear processes that have been operating in Betelgeuse's interior for millions of years. Professional astronomers worldwide will coordinate intensive observing campaigns to capture every aspect of the explosion's development. Radio telescopes will map the expanding shockwave as it sweeps up surrounding material, while infrared observations penetrate the dust clouds that may form as the explosion cools. Ultraviolet and X-ray telescopes will monitor the high-energy processes occurring in the shock-heated debris, providing insights into the extreme physics operating in supernova environments. Amateur astronomers will play crucial roles in documenting this historic event, contributing valuable, long-term monitoring data that complements professional observations. The supernova's brightness and extended duration will make it accessible to modest telescopes and even careful naked eye estimates, allowing citizen scientists worldwide to participate in studying one of nature's most spectacular phenomena. As weeks pass and the supernova begins its gradual decline from maximum brightness, the energy source powering its luminosity will shift from shock heating to radioactive decay. Unstable isotopes created during the explosion, particularly nickel-56, and its decay products, will provide the energy needed to keep the expanding debris hot and glowing for months or years. This radioactive decay phase offers unique opportunities to study explosive nuclear synthesis and measure the quantities of different elements produced during stellar death. The decline will be neither uniform nor monotonic. Careful photometric measurements will reveal fluctuations and periodicities in the light curve as different radioactive isotopes contribute varying amounts of energy over time. These observations will provide direct measurements of the nuclear inventory created during Betelgeuse's explosion, testing theoretical predictions about how shockwaves trigger nuclear reactions in stellar material. Advanced space-based telescopes will begin resolving the physical expansion of the supernova debris within months of the explosion, revealing the three-dimensional structure of the blast and any asymmetries created by rotation, magnetic fields, or interactions with circumstellar material. These high-resolution images will show individual clumps and filaments within the ejecta, tracking their motion and evolution as the supernova remnant takes shape. The search for the compact remnant left behind by Betelgeuse's core collapse will represent one of the most exciting aspects of post-explosion observations. If a neutron star forms, it may reveal itself as a pulsar, emitting regular beams of electromagnetic radiation as it spins. The detection and timing of these pulses would provide direct measurements of the neutron star's rotation rate, magnetic field strength, and potentially its internal structure. Pulsar timing observations represent some of the most precise measurements in all of astronomy, capable of detecting changes in rotation period smaller than parts per billion. These measurements probe the exotic physics operating inside neutron stars, where matter exists at densities exceeding atomic nuclei and magnetic fields reach strengths trillions of times greater than Earth's magnetic field. If Betelgeuse's core collapse produces a black hole instead of a neutron star, the observational signatures would be quite different but equally fascinating. Black holes cannot be detected directly through electromagnetic radiation, but their presence can be inferred through gravitational effects on surrounding material or through high-energy emissions from matter falling into their vicinity. The formation of a stellar mass black hole from Betelgeuse would represent one of the most massive such objects ever observed, providing crucial data about the relationship between stellar mass and core collapse outcomes. The expanding supernova remnant will continue evolving and providing scientific insights for centuries after the initial explosion. Computer models predict that the blast wave will sweep up increasing amounts of interstellar material over thousands of years, eventually accumulating several solar masses of gas and dust from the surrounding medium. This material will be heated, compressed, and accelerated by the ongoing expansion, creating the complex shell structures characteristic of mature supernova remnants. The interaction between the expanding debris and the interstellar medium will generate cosmic rays, high-energy particles that propagate throughout our galactic neighborhood for millions of years. These cosmic rays carry the chemical fingerprints of Betelgeuse's nuclear furnace, spreading the elements forged during the star's lifetime across vast distances and providing the raw materials for future planetary systems. Detailed studies of other supernova remnants, particularly the famous Crab Nebula created by a stellar explosion observed in 1054, provide previews of how Betelgeuse's explosion site will appear to future generations. The Crab Nebula continues expanding at over 1,000 kilometers per second, more than 9 centuries after the original explosion, powered by a rapidly spinning neutron star that creates complex filamentary structures throughout the surrounding debris. The educational impact of Betelgeuse's supernova will extend far beyond professional astronomy into classrooms and public outreach programs worldwide. This event will provide an unparalleled opportunity to demonstrate the connections between stellar evolution, nuclear physics, and cosmic chemical evolution using real-time observations rather than theoretical models or computer simulations. Students will witness the actual processes that created the elements in their bodies and enabled the formation of rocky planets throughout the universe. Science museums and planetariums will develop comprehensive programs to help visitors understand the significance of what they are observing. Interactive exhibits will demonstrate the scale of stellar explosions, the extreme conditions inside collapsing cores, and the role of supernova in dispersing heavy elements throughout galaxies. These educational efforts will help the public appreciate both the spectacular nature of the event and its profound importance for cosmic evolution. The global nature of supernova observations will emphasize the international character of modern astronomical research. Observatories on every continent will contribute data across the electromagnetic spectrum, while underground neutrino facilities and gravitational wave detectors provide complementary information about the explosion mechanism. This collaborative approach will generate datasets that astronomers will analyze for decades, gradually revealing new insights about stellar death and the exotic physics operating under extreme conditions. The technological capabilities available for studying Betelgeuse's explosion far exceed those that existed during previous nearby supernova. Modern detectors can measure radiation across wavelengths from radio waves to gamma rays, with sensitivities that would have seemed impossible to earlier generations of astronomers. Digital cameras and spectrographs will capture detailed records of the explosion's evolution with temporal and spectral resolution that enables unprecedented analysis of supernova physics. Machine learning algorithms are already being developed to help astronomers analyze the enormous datasets that will be generated by comprehensive supernova monitoring. These computational tools can identify subtle patterns and correlations in multi-wavelength observations that might escape traditional analysis methods, potentially revealing new aspects of explosion physics and stellar evolution that human observers alone could never discover. The chemical inventory dispersed by Betelgeuse's explosion will enrich the surrounding interstellar medium with elements essential for planet formation and potentially for life itself. Spectroscopic analysis of the expanding debris will reveal the quantities of carbon, oxygen, silicon, iron, and dozens of other elements produced during the star's lifetime and final explosive moments. These measurements will provide direct tests of stellar nucleosynthesis theory and improve our understanding of how different stellar masses contribute to galactic chemical evolution. The explosion will also produce significant quantities of radioactive isotopes that decay over timescales ranging from days to millions of years. Some of these, including aluminum-26 and iron-60, have been detected in meteorites and deep-sea sediments on Earth, providing evidence of past supernova explosions in our galactic neighborhood. Betelgeuse's contribution to this radioactive inventory will create isotopic signatures that may be detectable in future solar system materials, offering direct evidence of this specific stellar explosion's influence on our cosmic environment. The mixing and distribution of elements throughout the explosion debris will be governed by complex fluid dynamics as the expanding material encounters varying densities in the circumstellar medium. Rayleigh-Taylor instabilities and other hydrodynamic effects will create intricate structures that enhance the mixing of materials from different parts of the original star, determining how efficiently the supernova distributes its chemical products throughout the surrounding region. Long-term monitoring of the supernova remnant will track these mixing processes and reveal how quickly the newly created elements become available for incorporation into future stellar and planetary systems. The timescales involved span thousands to millions of years, requiring sustained observational programs that may continue for many human generations. These long-term studies will improve our understanding of how supernova contribute to the chemical evolution of galaxies and the formation of chemically diverse planetary systems. The gravitational wave observatories that have revolutionized astronomy over the past decade may detect signals from Betelgeuse's core collapse, providing entirely independent information about the explosion mechanism. While perfectly spherical collapse would produce no gravitational waves, realistic models predict that various asymmetries could generate detectable space-time ripples that reveal details about the core collapse process invisible to other observational techniques. The combination of gravitational waves, neutrinos, and electromagnetic radiation represents the multi-messenger astronomy approach that has already provided revolutionary insights into neutron star mergers and other extreme cosmic events. Betelgeuse's explosion will offer the first opportunity to apply this comprehensive observational strategy to a core collapse supernova, potentially revealing new physics and testing theoretical models with unprecedented precision. The cultural significance of witnessing a nearby supernova extends beyond scientific discovery into the realm of human experience and philosophical reflection. This event will provide a direct, visceral connection to the cosmic processes that created the elements essential for life and enabled the existence of rocky planets throughout the universe. Every person who observes the supernova will be seeing the very mechanism that forged the calcium in their bones, the iron in their blood, and the oxygen they breathe. The shared global experience of observing this spectacular astronomical event may foster greater appreciation for our common cosmic heritage and our place within a universe that continues creating and destroying on scales that dwarf human imagination. The supernova will serve as a reminder that Earth exists within a vast ecosystem where stellar birth, death, and renewal drive the ongoing evolution of chemical complexity and the conditions necessary for life. Historical records of previous naked-eye supernovae reveal that these events have often influenced human culture and scientific understanding in profound ways. The supernovae observed in 1572 and 1604 challenged the Aristotelian view that the heavens were unchanging and eternal, contributing to the scientific revolution that transformed our understanding of the cosmos. Betelgeuse's explosion will likely have similar impacts on contemporary culture, demonstrating the dynamic nature of the universe and our intimate connection to stellar evolution. The timing uncertainty surrounding Betelgeuse's explosion means that any generation could witness this remarkable event. Current observations cannot predict whether the supernova will occur within the next few years or several millennia from now. This uncertainty adds an element of anticipation to continued monitoring of the star, as each brightness fluctuation or spectroscopic change could potentially signal the beginning of the final collapse sequence. Regardless of when it occurs, Betelgeuse's supernova will represent one of the most significant astronomical events in human history. The combination of proximity, brightness, and duration will provide opportunities for detailed study that may never be repeated. Future generations will inherit both the spectacular visual legacy of this cosmic explosion and the scientific knowledge gained from observing stellar death with unprecedented detail and precision. The neutron star, or black hole, that remains after the explosion will continue influencing its cosmic environment for millions of years, serving as a source of high-energy radiation, cosmic rays, and potentially gravitational wave signals. These compact objects represent the ultimate products of stellar evolution, creating conditions so extreme that they test the fundamental limits of our understanding of matter, energy, and space-time itself. Future space missions may eventually visit the Betelgeuse supernova remnant directly, using advanced propulsion technologies to study the explosion site and its central compact object at close range. Such missions would provide unprecedented detail about the explosion's three-dimensional structure and the properties of matter under the most extreme gravitational conditions in the universe. These observations could revolutionize our understanding of fundamental physics and the role of stellar death in cosmic evolution. The knowledge gained from studying Betelgeuse will inform our interpretation of stellar explosions observed throughout the universe. Distant supernovae appear as brief flashes of light that provide limited information about explosion mechanisms and stellar properties. The detailed observations possible for a nearby event like Betelgeuse will provide crucial calibration data for understanding these more distant explosions and their contributions to cosmic chemical evolution and galaxy formation. As we continue monitoring Betelgeuse and preparing for its eventual explosion, we participate in one of astronomy's most exciting ongoing investigations. This red supergiant represents a natural laboratory for studying extreme stellar physics under conditions that reveal fundamental truths about how massive stars live, die, and enrich the cosmos with heavy elements. The explosion, whenever it occurs, will provide answers to questions that have puzzled astronomers for generations, while undoubtedly raising new mysteries that will drive future research. The story of Betelgeuse reminds us that we inhabit a universe where apparently stable objects undergo dramatic transformations over cosmic timescales. Stars form from collapsing gas clouds, burn through their nuclear fuel according to the laws of physics, and die in spectacular explosions that seed space with materials necessary for planets and life. These cycles of stellar birth, evolution, and death have operated for billions of years, gradually increasing the chemical complexity of the universe and creating the conditions that made our existence possible. When Betelgeuse finally explodes, it will add another chapter to this ongoing story of cosmic evolution, demonstrating once again that we live in a dynamic universe where creative and destructive processes operate on scales that challenge human comprehension. The explosion will serve as a powerful reminder that Earth and its inhabitants exist within a vast cosmic ecosystem where stellar death enables new forms of complexity and beauty to emerge across the immense spans of cosmic time. The electromagnetic cascade that follows Betelgeuse's core collapse will create a spectacle that fundamentally challenges our understanding of stellar death, while simultaneously confirming decades of theoretical predictions about how massive stars meet their end. As the shockwave races outward through the star's layered structure, it will encounter regions of dramatically different density and composition, each interaction producing distinctive observational signatures that reveal the internal architecture of this stellar giant. The helium-burning shell surrounding the inert core will be the first to feel the shockwave's devastating impact. Here, temperatures will spike beyond 10 billion degrees as the rebounding energy compresses and heats material that has been quietly fusing helium into carbon for thousands of years. This sudden heating will trigger explosive helium burning, releasing additional energy that amplifies the shockwave's power and contributes to the overall luminosity of the explosion. Moving outward through successive layers, the shock will encounter the hydrogen-burning shell that has been Betelgeuse's primary energy source for millions of years. The collision between shock-heated material and the relatively cool hydrogen envelope will create a complex interface where rapid nuclear reactions produce a flood of gamma rays and high-energy particles. These emissions will provide astronomers with direct evidence of the nuclear processes occurring during explosive stellar death. The shockwaves' journey through Betelgeuse's extended atmosphere will take hours rather than the milliseconds required for core collapse, allowing detailed observations of how stellar explosions develop and propagate. Space-based X-ray telescopes will detect the characteristic radiation signatures as different atmospheric layers reach shock-heating temperatures, creating a temporal map of the explosion's progress through the star's interior structure. Ground-based observatories equipped with rapid response systems will begin detecting optical brightening within hours of the neutrino burst as the shockwave finally breaks through the stellar photosphere and releases the trapped energy into space. This shock breakout marks the moment when Betelgeuse transforms from a red supergiant star into a brilliant supernova visible across interstellar distances. The initial optical flash will be dominated by blue and ultraviolet wavelengths as the shock-heated material reaches temperatures exceeding 50,000 degrees. This intense radiation will ionize any remaining hydrogen in the star's outer atmosphere, creating a plasma envelope that glows with characteristic emission lines, revealing the chemical composition of Betelgeuse's surface layers. Professional astronomers have already established detailed observing protocols for this eventual event, with automated alert systems designed to notify research facilities worldwide within minutes of the first detection. Major observatories will implement coordinated campaigns to capture the explosion's development across multiple wavelengths simultaneously, ensuring comprehensive coverage of this once-in-a-lifetime astronomical event. The European Southern Observatory's Very Large Telescope Array will provide high-resolution spectroscopy to measure the velocities and temperatures of material ejected during the explosion. The Atacama Large Millimeter Array will map the distribution of molecules and dust in the expanding debris. Space-based facilities, including the James Webb Space Telescope, will penetrate any dust clouds that form around the explosion site, revealing the internal structure of the supernova ejecta. Amateur astronomy communities worldwide have prepared observing guidelines to help citizen scientists contribute meaningful data to professional research efforts. The supernova's brightness and extended duration will make it accessible to modest telescopes, allowing thousands of observers to participate in documenting this historic event through coordinated photometry and imaging programs. The spectroscopic signatures emerging from Betelgeuse's explosion will provide direct measurements of the star's pre-explosion composition and structure. Absorption lines from hydrogen, helium, carbon, oxygen, and heavier elements will reveal how these materials were distributed throughout the stellar interior before core collapse. The relative strengths and velocities of these spectral features will test theoretical models of how massive stars evolve and stratify their composition during their final evolutionary phases. Doppler shift measurements of the expanding debris will map the three-dimensional structure of the explosion, revealing whether the shockwave propagated symmetrically or developed significant asymmetries due to rotation, magnetic fields, or interactions with circumstellar material. These observations will provide crucial tests of supernova explosion models that have been developed through decades of computer simulations. The radioactive decay phase that powers the supernova's sustained luminosity will offer unique opportunities to study explosive nuclear synthesis in real time. As unstable isotopes created during the explosion decay into stable elements, they will release energy that keeps the expanding debris hot and luminous for months or years. The specific decay rates and energy releases will provide direct measurements of the nuclear inventory produced during Betelgeuse's death. Gamma-ray telescopes will detect the characteristic radiation signatures from radioactive decay, particularly the distinctive 1.238 mega-electron-volt line from cobalt-56 decay that powers many supernova-like curves. These observations will reveal how efficiently the explosion mixed different layers of the stellar interior and distributed radioactive materials throughout the ejecta. The decline phase observations will also search for evidence of dust formation within the cooling supernova debris. As temperatures drop below several thousand degrees, refractory elements like carbon and silicon may begin condensing into solid grains, creating the cosmic dust that serves as raw material for future planetary systems. Infrared observations will track this dust formation process and measure the quantities of solid material produced by the explosion. Long-term monitoring programs will follow the supernova's evolution through its transition from explosion to supernova remnant. As the expanding shockwave sweeps up increasing amounts of interstellar material, it will create the characteristic shell structures observed in mature remnants like the Cygnus Loop and Veil Nebula. These observations will reveal how supernova explosions shape and energize the interstellar medium. The search for Betelgeuse's compact remnants will represent one of the most challenging aspects of post-explosion observations. If core collapse produces a neutron star, it may remain hidden within the bright supernova debris for years or decades before becoming detectable as an isolated pulsar. Radio telescopes will conduct systematic searches for the periodic signals that would indicate a rapidly spinning neutron star at the explosion center. Pulsar discoveries require exquisite timing precision to detect the regular pulses of electromagnetic radiation emitted by rotating neutron stars. The most sensitive radio telescopes can measure pulse arrival times to accuracies of microseconds, revealing details about neutron star rotation, magnetic field strength, and potentially the exotic physics operating inside these ultra-dense objects. If Betelgeuse's core collapse produces a black hole instead of a neutron star, the observational signatures will be quite different but equally scientifically valuable. Black holes cannot emit regular pulses like pulsars, but they can be detected through their gravitational effects on surrounding material or through high-energy radiation from matter falling into their vicinity. The formation of a stellar mass black hole from Betelgeuse would provide crucial data about the relationship between stellar mass and the outcomes of core collapse. The expanding supernova remnant will serve as a natural particle accelerator for millions of years after the initial explosion. As the shockwave encounters the thin gas filling interstellar space, it will accelerate charged particles to enormous energies, creating cosmic rays that propagate throughout our galactic neighborhood. These high-energy particles will carry the chemical fingerprints of Betelgeuse's nuclear furnace across vast distances. Cosmic ray observatories on Earth and in space will detect the arrival of these particles years or decades after the optical explosion, providing direct samples of material processed in Betelgeuse's interior. The energy spectrum and composition of these cosmic rays will reveal details about the acceleration mechanisms operating in supernova shockwaves and the propagation of high-energy particles through interstellar magnetic fields. The heavy elements dispersed by Betelgeuse's explosion will gradually mix with the surrounding interstellar medium, enriching it with carbon, oxygen, silicon, iron, and dozens of other elements essential for planet formation. Spectroscopic surveys of nearby gas clouds will track this chemical enrichment process, revealing how efficiently supernovae distribute their nuclear products throughout galactic regions. Future generations of stars forming in this enriched environment will incorporate Betelgeuse's nuclear legacy into their planetary systems. Rocky planets orbiting these future stars will contain materials forged in Betelgeuse's core and explosive death, continuing the cosmic recycling program that has gradually increased the chemical complexity of our galaxy over billions of years. The educational impact of Betelgeuse's supernova will extend far beyond astronomy into physics, chemistry, and earth science curricula worldwide. This event will provide real-time demonstrations of nuclear fusion, radioactive decay, shockwave physics, and electromagnetic radiation across the spectrum. Students will witness the actual processes that created most elements heavier than hydrogen and helium, connecting abstract nuclear physics concepts to observable cosmic phenomena. Science museums and planetariums will develop immersive programs to help visitors understand the scale and significance of stellar explosions. Interactive exhibits will demonstrate the extreme conditions inside collapsing cores, the vast energies released during nuclear fusion, and the role of supernovae in creating and distributing the elements necessary for rocky planets and biological chemistry. The global coordination required for comprehensive supernova observations will showcase the international nature of modern astronomical research. Data sharing protocols already exist to ensure that observations from facilities worldwide can be combined and analysed collaboratively. This coordinated approach will generate datasets of unprecedented completeness and quality. Advanced computational techniques are being developed to analyse the enormous volumes of data that will be generated by multi-wavelength supernova monitoring. Machine learning algorithms can identify subtle patterns and correlations in spectroscopic observations that might escape traditional analysis methods. These computational tools will help astronomers extract maximum scientific value from every photon detected during Betelgeuse's explosion. The technological capabilities available for studying this supernova far exceed those that existed during previous nearby stellar explosions. Modern detectors can measure radiation across wavelengths from radio waves to gamma rays, with sensitivities that enable detection of extremely subtle features in supernova spectra. Digital recording systems can capture data continuously rather than relying on photographic plates or single measurements. Space-based observatories provide access to wavelength regions blocked by Earth's atmosphere, particularly in the ultraviolet and X-ray portions of the spectrum, where many important atomic transitions occur. These space telescopes will observe the supernova without atmospheric interference, providing cleaner data for testing theoretical models of explosion physics and stellar evolution. The neutrino detection capabilities that will provide early warning of Betelgeuse's core collapse represent remarkable achievements in experimental physics. Underground facilities containing thousands of tons of ultra-pure detection media can register individual neutrino interactions despite the extraordinary rarity of these events under normal conditions. The flood of neutrinos from core collapse will overwhelm these detectors temporarily, providing detailed records of the collapse process. Multiple neutrino observatories distributed around the globe will provide independent confirmations of the core collapse event and enable detailed analysis of the neutrino burst's temporal and energy structure. Differences in arrival times at different facilities will help determine the exact moment of core collapse and potentially reveal asymmetries in the explosion mechanism. The gravitational wave observatories that have revolutionized astronomy over the past decade may detect spacetime ripples from Betelgeuse's core collapse. While perfectly spherical collapse would produce no gravitational waves, realistic models predict that various asymmetries could generate detectable signals. These observations would provide entirely independent information about the core collapse process that complements electromagnetic and neutrino detections. The multi-messenger astronomy approach, combining gravitational waves, neutrinos, and electromagnetic radiation, will reach full maturity with Betelgeuse's explosion. This comprehensive observational strategy has already provided revolutionary insights into neutron star mergers and other extreme cosmic events. A nearby core collapse supernova will offer the first opportunity to apply these techniques to stellar death, potentially revealing new physics and testing theoretical models with unprecedented precision. The chemical inventory created during Betelgeuse's explosion will include isotopes with a wide range of stability and decay characteristics. Some radioactive species will decay within days or weeks of formation, contributing to the supernova's early luminosity. Others will persist for thousands or millions of years, gradually enriching the interstellar medium with stable elements as they undergo radioactive decay. Detailed nuclear physics calculations predict the specific isotopic ratios that should be produced during explosive nucleosynthesis in massive stars. Betelgeuse's explosion will provide direct observational tests of these predictions, potentially revealing gaps in our understanding of nuclear reactions under extreme conditions or confirming theoretical models with unprecedented precision. The dust formation process within the cooling supernova debris will create the raw materials for future planetary systems. As temperatures drop below condensation thresholds for different elements, solid grains will begin forming from the gas phase materials ejected during the explosion. This dust production represents a crucial step in the cosmic recycling program that supplies heavy elements to star-forming regions. Infrared observations will track the dust formation process in real time, measuring the quantities and compositions of solid particles created as the supernova cools. These measurements will improve our understanding of how supernova contribute to the cosmic dust budget and provide materials for planet formation in future stellar systems. The hydrodynamic evolution of the expanding supernova remnant will create complex three-dimensional structures as the shockwave encounters density variations in the surrounding interstellar medium. Rayleigh-Taylor instabilities and other fluid dynamic effects will generate the filamentary structures and shell morphologies characteristic of mature supernova remnants. High-resolution imaging of the developing remnant will reveal these structural details and test theoretical models of supernova hydrodynamics. Computer simulations of remnant evolution can be compared directly with observations, providing crucial validation of the numerical techniques used to model these complex systems. The long-term influence of Betelgeuse's explosion on the surrounding galactic region will extend far beyond the immediate supernova remnant. The energy and momentum injected by the explosion will drive turbulence in the interstellar medium, potentially triggering or suppressing star formation in nearby molecular clouds. These effects help regulate the rate of stellar birth throughout galaxies. The cosmic ray particles accelerated by the supernova shockwave will propagate through the galaxy's magnetic field for millions of years, carrying energy and chemical information across vast distances. These particles contribute to the heating and ionization of the interstellar medium while providing a probe of galactic magnetic field structure and strength. Future observations of the Betelgeuse explosion site will continue revealing new aspects of supernova physics for decades or centuries after the initial event. As the remnant ages and evolves, it will transition through different phases of development, each offering unique insights into the long-term consequences of stellar death and the ongoing processes that shape galactic evolution. The scientific legacy of Betelgeuse's supernova will influence multiple areas of astrophysics research for generations. The detailed observations possible for this nearby explosion will provide calibration data for interpreting more distant supernova observed in external galaxies. These distant events appear as brief flashes of light that provide limited information about explosion mechanisms and stellar properties. The knowledge gained from studying Betelgeuse will improve our understanding of how supernovae contribute to galactic chemical evolution and the formation of successive generations of stars and planets. This research has direct implications for understanding the conditions necessary for life to emerge and evolve on planetary surfaces throughout the universe. The technological developments driven by preparations for observing Betelgeuse's explosion will benefit many areas of astronomy and physics. Advanced detectors, data analysis techniques, and computational methods developed for supernova research find applications in studying other astronomical phenomena and fundamental physics experiments. The cultural impact of witnessing this cosmic spectacle will extend far beyond the scientific community. The supernova will provide a shared global experience that transcends national and cultural boundaries, offering opportunities for reflection on humanity's place within the vast cosmic ecosystem that continues creating and destroying on scales that dwarf terrestrial experience. The timing uncertainty surrounding Betelgeuse's explosion ensures that this event could occur during any generation's lifetime. Current observations cannot predict whether the supernova will happen within years or millennia, creating an ongoing sense of anticipation within the astronomical community and the general public alike. Regardless of exactly when it occurs, Betelgeuse's explosion will represent one of the most significant astronomical events in human history. The combination of proximity, brightness, and scientific importance will provide opportunities for discovery and education that may never be repeated. This cosmic event will serve as a powerful reminder that we inhabit a dynamic universe where the death of stars enables the birth of new complexity and beauty across the immense expanses of cosmic time. The elements forged in Betelgeuse's nuclear furnace and dispersed by its explosive death will eventually find their way into new stellar and planetary systems, carrying forward the chemical legacy of this remarkable star. Future civilizations that may arise around stars enriched by Betelgeuse's supernova will owe their existence partly to the nuclear processes we will witness when this stellar giant finally reaches the end of its magnificent cosmic journey. So there you have it, the complete story of Betelgeuse, from the fears that grip our imagination to the magnificent reality that awaits us. When this stellar giant finally does explode, it won't herald the end of our world, but rather one of the most spectacular beginnings in scientific history. Earth will remain safely nestled in its cosmic harbour, protected by the vast distances of interstellar space, while we witness the universe's most powerful forge, creating the very elements that make life possible. The neutrinos will arrive first, flooding our underground detectors with ghostly messengers from the collapsing core. Hours later, a new star will blaze forth in Orion's shoulder, shining bright enough to cast shadows at midnight and remain visible throughout the day. For months, this cosmic beacon will remind every person on Earth that we are intimately connected to the stellar processes that created the calcium in our bones, the iron in our blood, and the oxygen we breathe with every breath. Whether Betelgeuse explodes tomorrow or in 1,000 years, its eventual supernova will represent far more than just another astronomical event. It will be the universe demonstrating its capacity for both destruction and creation on scales that humble human imagination, while simultaneously revealing the profound connections that link our existence to the death of stars. When that moment comes, we won't be witnessing the end of something, but rather the beginning of countless new possibilities scattered across space and time. Tonight, as you step outside and look up at that familiar red giant glowing in Orion's embrace, remember that you're gazing at one of nature's most magnificent time bombs, counting down toward a cosmic explosion that will illuminate our understanding of how the universe creates complexity and beauty from the ashes of stellar death. Until that spectacular moment arrives, Betelgeuse continues its ancient vigil, a stellar lighthouse marking our place in a cosmos where every ending becomes a new beginning.